And welcome once again for another advanced engineering video. This is day 2, part A, and we're going to start off by discussing exact ODEs. So exact differentials. The total differential, we can recall from multivariable calculus, that total differentiation has something like this, looks something like this. So this is like a multivariate thing, right? So we have a function u of xy, and the total differential is du, so taking the derivative of the function u here is going to be equal to the partial derivative of u with respect to x times dx plus the partial derivative with respect to y of dy. And the reason for this has to do with continuity. Now, there's something continuity in both dimensions, right? So you can go. This is why we need this fact to be true. Now, what you can do is you can look at the constants, the line of constants here for the function. So if the function u is equal to some constant value rather than some random functional, then we can actually do something that's quite useful, and set du equal to 0. Okay, and this should be obvious. When you take the derivative of a constant, it's equal to 0, something that you know. Now, here's an example of having some kind of function of x and y equal to some constant. So we have this function x plus x squared times y cubed, right? This is a function of x and y. And we're going to set it equal to the constant c like we were doing above. We can actually then figure out these partial derivatives, right? We've now set the function to be something. It's x plus x squared y cubed. And now if I take the derivative with respect to x, that means holding y constant. Then obviously the first part is just 1 because ddx of x is 1. And then the second part, it's 2xy cubed, which is what we get here. And similarly, I can take the partial derivative with respect to y, which is what I do here. I get 3x squared y squared. Then what I'm left with is I've actually found this total differential, right? The total differential is this following piece here. Now this actually, by the way, this kind of formulation ends up being really useful in various fields of physics. One that really especially stands out in the mind is in thermodynamics, because you deal with total differentials there and exact differentials as we get to that in a moment, quite frequently, because you need to have multiple variables. Depending on the assumptions made, you need at least 2 variables in thermodynamic analysis. If you have you might have other situations where you need more than 2, but at the very bare minimum, you need 2 variables to describe an entire thermodynamic state. And so that's an example of something that would where a total differential like this would be useful. Now we can take this further, and we can actually figure out what the derivative dy dx is. So again, this is quite useful because notice that now if you follow this line of reasoning, I can actually figure out what dy dx is, at least the implicit version of dy dx here, right? So dy dx is equal to minus 1 plus 2xy cubed divided by 3x squared y squared, if you follow the full line of reasoning here, just by rearranging that du that we had above. So this is incredibly useful if we have, if we can figure out that our function is equal to some constant, then we can actually work our way back to a nice differential equation that we found down here. So why is this important? Well, as you'll see as we move later on into this video, you can actually use this fact to help solve first order differential equations. And basically this is going to lead, just to foreshadow what we're going here into, this is going to lead into the integrating factor. So we're going to be able to actually show that we should be able to arrive at an integrating factor, and in most cases, not in every possible case, but in most cases, there's a simplified, or in most cases that we'll see at least, there's a simplified version of the integrating factor where we assume that the integrating factor is only a function of one variable that will be very useful for first order differential equations, ordinary differential equations. So this actually is going to end up being very powerful. So how do we do this? Well, we start off with a potentially exact, and I'll tell you what I mean in a moment by potentially, a potentially exact differential equation. So we write it in a form like this down here. So we have m of xy times dx plus n of xy times dy equal to 0. Now if I go up here, I can actually see this would have been my m, this would have been my function m, and of course it's a multivariate function, and it's a function of both x and y. This would have been my function n in this example. So we write it in this way, and how do we tell if it's an exact differential equation? Well, first of all, we're going to know that u has to be equal to c because of this 0 over here. That tells us that u must be equal to some constant, which is again useful for our purposes. And we set du dx equal to m of xy. This obviously is du dx here. We set du dy equal to n of xy. And to test exactness, what we do is we take the partial derivatives dm dy and set it equal to the partial derivative of dn dx. This is both necessary, this fact is both necessary and sufficient to be an exact differential. So we start off with something that's potentially exact. We don't know that it's exact, but it's potentially exact. And the condition ends up being that if we take this m and we take the partial derivative of it with respect to y and set it equal to the partial derivative of this with respect to x, this function n with respect to x, if the two of them happen, if that is a true equation, if they are in fact equal to each other, then we know it is an exact differential equation, ordinary differential equation, exact differential equations, excuse me. This actually then allows us to get into implicit form at least the equation. So how can we go about this? Well, we know that du dx is equal to m, so that means that we can actually integrate both sides of this. And so what we find is that u must be equal to m dx plus k of y. Similarly, we can use n, because we know n is equal to du dy. So we can integrate this. we can use this already used fact down here, and we can get the implicit. We can find the implicit version of the function this way. So basically, we integrate. We integrate first with the part with m. Then we can integrate the part. We can integrate the part with this. Right. We take dy of the integral here. Because we're just distributing the partial derivative through, and we can use this to help us find this function k that we were talking about here. K is only a function of y, notice, because when I integrated it, it couldn't have been, if it didn't end up inside of the integral with the dx, then it couldn't have been a function of x, right? So what we can then do, I'm going to actually give an example of this, because this is kind of obtuse, the way that we have this written here, right? Okay, we're integrating this, whatever this function m is, but it's kind of hard to see how this maps out with an actual function, and the same thing with n. So let's actually do an example. So the first thing is I want to test for exactness. Now remember, we said exactness can be tested by exactly doing this, dm, dy, and dn, dx. So we have to actually find m and n. We have to figure out what m and n are. Excuse me. And then we can do this process to get our implicit. So we integrate first, and then we take the derivative here with respect to y, and we'll be able to find our function u that way. Okay, so first let's test for exactness. What we have here is we have this function x cubed dx plus y cubed dy. Well, notice that we're going to switch colors here just so that we can have something different. Notice that this must be my m, and this must be my n, right? Based on our writing of total differentials up here, the potentially exact differentials up here, whatever is in front of the dx is m, whatever is in front of the dy is n. So we come down here, and that's what we have. We have m and n. Now notice that in this particular case, they're actually only functions of a single variable. That's not always going to be the case, but that's true in this case here. Now we want to test for exactness. So we said m is equal to x cubed and n is equal to y cubed. Well, if I take the derivative of m with respect to y, holding x constant, well, if x is a constant, there's no y in here, so the derivative must be 0, right? And similarly, the derivative with respect to x of n must be 0 because y is being held constant. So we get both of them are 0, which means this is exact. It has to be exact, right? So now we can actually solve. We can get the implicit equation for u, the function u. So remember that what we did up here was we said, okay, well, we know that this is du dx must be m. So because of that, excuse me, so because of that, we can now do this integration, right? We know that m is equal to du dx. So now we're going to integrate both sides. We're going to get u is equal to the integral of m dx. Well, m, remember, up here is x cubed. So we're going to say the integral of x cubed dx for this part plus k of y. Okay, so let's figure out what that is. Well, if that's the case, the integral of x cubed dx is just x to the fourth over 4, right? And so we get x to the fourth over 4 plus k of y. Now we have to take to finish this whole thing off. Remember we said, okay, now it also has to satisfy this piece with n, so we can actually figure out what k of y must be. We're going to take the derivative with respect to y here, which is the same as n, and du dy must be equal to y cubed, because we said n was y cubed, right? So we know that du dy, n, and y cubed are all the same thing in this example. Very good. So if we take that partial derivative, what we end up with is dk dy has to be equal to y cubed. Why is this the case? Why isn't there another term? Well, obviously, if I take the derivative of x with respect to y when x is being held constant, that goes to 0. So that's why we're left with just dk dy in this case, right? Because we took the derivative with respect to y. And again, we know that n was equal to y cubed. So du dy is equal to dk dy in this particular case, which is equal to y cubed. Now, notice that this is a full derivative and this is a partial derivative. And you say, well, why is that? Well, because remember that k is only a function of y. So because it's not multivariate function, this has to be a full derivative. Okay, and then we can actually figure out what k must be, right? Because we know dk dy is equal to y cubed, so we can just, this is actually a nice separable differential equation. You can just multiply the dy over and integrate both sides, which is what I do here. And you get y to the fourth over 4 plus c. So basically that tells me that u has to be equal to x to the fourth over 4. That's that first part, the integral of m dx part. And the k of y is this y to the fourth plus over 4 plus c. We can actually check this solution. If I take the derivative with respect to x, well, c is a constant, so that goes to 0, and I just get x cubed. Over here, I get du dy is equal to y cubed. So it is, upon checking the solution, we have found the correct solution, right? So we know that u must be this function, x to the fourth over 4 plus y to the fourth over 4 plus c. So this is really useful way of figuring out what the function must be. Now we can do I'm going to do a different example, and the idea here is just to point out which functions are not, some functions may not actually be exact. So in this case, it's not exact, and you'll see in a moment that this is true. Okay, so my m here, because it's the term that goes in front of the dx, is x minus y. My n here is also x minus y, because that's the term that goes in front of the dy, and it's equal to 0. So we're potentially in exact form, but notice that if I take the derivative with respect to y here, well, x is held constant, so that's 0, so we get minus 1 for that derivative, but we get a plus 1 for this derivative. And since this is not the case, negative 1 is not equal to 1, then this differential is not exact. Okay, so this is an example where we get something that's not exact, and we're actually going to return to this example in a moment. Integrating factors. Okay, so I mentioned that integrating factors were going to become important. So the idea is that we can actually turn an equation that's not exact into one that is exact. And this works for a wide array of functions. Here's an example. We have minus y dx and x dy plus x dy is equal to 0. This is not exact because dm dy is equal to minus 1. dn dx is equal to 1. So kind of like the example above, it shows that it's not exact. But notice that if I multiply both sides by 1 over x squared, which is right, since I'm multiplying both sides of the equal sign by this, it's the same as multiplying by 1. If I do that, then what I find is I have minus y over x squared here and 1 over x here as my m and n. And if I take the partial derivatives there, they actually end up being the same in this case. So I multiplied by this function, and all of a sudden it became exact. This is the idea for integrating factors. We can actually take inexact equations and make them exact. Now, if we go to the thermodynamics example, because I've been talking about thermodynamics, the thermodynamics example, there is actually something in thermodynamics that behaves like this, and it's called the entropy. So basically, the why we care about exactness, by the way, is that inexact differentials actually are path dependent. So this is really crucial. That means that when we integrate, we have to actually care about the path that's taken from A to B, rather than just the endpoints, which is obviously a pain in the neck, and we prefer not to have to worry about the path, because that's the whole point in calculus, right? And in calculus, we only care about the endpoints. In calculus 2, for instance, when we first start dealing with the integral, we only care about the endpoints. In fact, we write the endpoints right on the integral when we have them, right? If we're dealing with something that has actual values that we can work with, and so this idea of exactness is really important and crucial in that sense. So we actually know how to perform the integral, for instance. And it turns out in thermodynamics that there are a couple of quantities that are not exact, and one of them is heat. So heat, we actually have to care about the path, but the key there is that we've figured out a way to make that exact. And the way to do it is to multiply by 1 over the temperature. So if we multiply, so the integrating factor in that case is 1 over t. If we multiply by 1 over t, suddenly the inexact heat becomes exact, and this is the entropy. So it's a really crucial and important concept. So this isn't just this stuff extends to important areas beyond just mathematics. Now, why do we care about the integrating factor? Well, I just kind of mentioned there, once we have exactness, that makes our life easier for solving things. But we can actually use the integrating factor to help us find the solution. For instance, in this particular case, we now have, we can actually integrate both sides here. So the integral of minus y over x squared dx plus the integral of 1 over x dy. Well, if you notice, this becomes the integral of this first part becomes 1/2 y over x. The integral of this part, because it's integrating with respect to y, becomes y over x. and then that's going to be equal to c because the integral of 0 is c. So I'm not going to change c here because I have this, when I add these two together, I get 3/2 y over x. So if I divide over the 3/2, I just get y over x is equal to c, and this is my general solution. So this is really powerful technique. This allows us to actually find the solution, general solution to these kinds of differential equations. Now, the general method of the integrating factor follows this exact path that we just did. We start off, now instead of being n and m, we have p and q. Don't ask me why the book decided to change course here. I think it's just to highlight that this is different. This ends up being different because, in some ways, because m and n are, we're assuming that we can make them into exact. So we want f times p to be n, and we want f times q to be m. I think this is why your book does it this way. But in any case, we have p of xy dx plus q of xy dy is equal to 0. Again, potentially an exact form, but we're saying, what if it's not exact? Well, we can find this function, and in general, keep in mind, in general, this function is going to be a function of both variables, x and y. In a moment, we're going to make an assumption, but that assumption doesn't apply to every possible scenario, and I'll show you an example of that in a moment. But f times p becomes my m, and f times q becomes my n, right? So now in this case, we're looking for this function that we can multiply times both of these terms, the p and the q terms, such that it turns it into an exact equation. And I'll note that if it's already exact, you say, well, what if it's already exact, right? Well, we just have to choose f to be equal to 1, right? Then we're good. So nothing is, in that case, nothing's violated there. We can choose this function to be a constant if we need to. Now, how do we find this integrating factor? Well, what we're going to do is we're going to obviously take advantage of the fact that this is the truth for exactness, right? dm dy has to be equal to dn dx. So if I take d dy of fp, this is my m, it has to be equal to d dx of fq. That's my n, like we said. If we take the product rule, right, because we have the product of two functions now, we take the product rule, df dy times p plus dp dy times f, right, because we're splitting the two using the product rule. The product rule says it's the sum of the derivative of one function times just the other function, plus the derivative of the other function times the original function, right? So this is the product rule. And similarly, we have to apply the product rule to this side. And so this basically is our rule, right? We end up saying, okay, let's find an f that does exactly this. Well, I hope you can see that there's no apparent straight way forward here. Like, how do we find f? However, if we make a further assumption, and this is, again, this simplifies our problem, but it doesn't apply in all cases, so we can't always do this. But it simplifies our problem if we assume that the function f is only a function of a single variable rather than both variables, multiple variables, right? So if I do that, notice that if I assume that it's just a function of x, we can also do just a function of y, by the way, and the process ends up working out exactly the same. It's just depends on which terms end up staying in, the the partial derivatives with respect to y, or the partial derivative with respect to x, right? But notice that if f is only a function of x, well, when I take the derivative of that with respect to y, it's 0, so that term falls away. So this very first term is going to actually fall out of the equation, and we'll see that that makes life easier. And that's exactly what I'm showing here. F is only a function of x. We've simplified it. There, one of the terms went away. And we can do this fun game. It's just an algebraic one. But so, you know, dividing things, subtracting things, whatever, over. But at the end, we end up getting that this is the case. Okay, so we get equation 7 out of this. And I encourage you to walk your way through each of those steps, but it's fairly easy. And what we get is this term, we're going to call it R, just to make our lives easier, because it's a pain in the neck to write out this every time. And if we set this equal to R, then we can just say R is equal to the right-hand side, the 1 over f df dx. Now notice this is a full derivative again because f is only a function of x. Great. So we know that this is now true. I'm just rewriting it, rearranging it. And what I can do then is this is now separable, which makes my life easy. There's no f in here. So because there's no f in that function r, this is nicely separable. So I have df over f, and I can multiply the dx over. Now r could be a function of both x and y, right? That's possible. So in general, r is a function of x and y. But it does not have f in it. Great. So now what I can do is df over f. Well, if I integrate this, that just becomes the natural log of f. And I integrate the other side, and I get the integral of r dx. Since I don't know what the function r is, that's as far as I can simplify it, right? I can integrate it once I know what the function r is, but that's as simple as I can make it. But then, if I want to figure out what f is, it's got to be equal to e to the integral of r dx. So this is why the integrating factor has an exponential in it. All right, it's kind of simple to follow the logic here. Now, I wanted to point out, again, the key piece here is that this is not always going to work. And let's see an example. Well, we already saw this example, actually. We determined that this is not exact. So first of all, since it's not exact, we determined that earlier up here, that this is not exact. Right? Not exact, same function. So what I can try to do then is the integrating factor. So what I'm going to do is I'm going to say, okay, well, my q is x over y, x minus y. My p is also x minus y. If I can take the partial derivatives here, because, right, this is dp dy. Well, dp dy is -1. Right, because the derivative of this with respect to y, there's a minus sign there, so it's -1. dq dx is just plain 1, so when I subtract those two based on our formulation up here, right here, I have to subtract them, right? This was just algebraically, we proved this. Then I get -2 here. And then I have to multiply by 1 over q. This is my 1 over q, this term right here. So I get -2. I'm going to show you over here. I get -2. Oops. -2 over x minus y. Okay. And then this becomes my integrating factor. I just get f of x is equal to the integral of r, which is -2 over x minus y times dx. that has to be equal to the integral of e to the minus 2 natural log of x minus y. I do some, I move the 2 into the exponent here, and then at the end, e to the log, well, this is minus log, so the e to the minus log means I have to do, I have to take the reciprocal of it when I move it down, so it becomes 1 divided by x minus y squared. Now, this is my integrating factor according to this approach, assuming that it's a single variable integrating factor. But notice that if I check the exactness here, what you'll find is that it's not exact. So I multiplied by this is my f, 1 over x minus y squared times x minus y. And what you find is that we get the derivative here on the left-hand side is 1 over x minus y squared, but the derivative on the other side is minus 1 over x minus y squared. So they're not equal to each other, so it's still not exact. So this is an example of a case where we would actually need f of xy if we were going to find an integrating factor. We can't do a single variate case of the integrating factor. So do be careful. It's not always going to apply, but it mostly does. And that's all that I have for this video. Hope to see you again soon.